Rongcheng, currently a doctoral student in Osaka University, Japan. In this video, I will introduce the paper Loosely Stabilizing Maximal Independent Set Algorithms with Unreliable Communications. The authors of the paper include me, Dr. Yuichi Sudo, Professor Taisuke Izumi, and Professor Toshimitsu Masuzawa. The presentation includes 5 parts: a brief introduction of the paper, the description of problem we try to solve, the contribution we made, the loosely stabilizing approaches we proposed in this paper, and the summary and future work. First, let me give the introduction of the paper. In this part, I will briefly introduce the notions of self-stabilization and loose-stabilization. The notion of self-stabilization is first proposed by Dijkstra in 1974. In his pioneer work, he introduced the first self-stabilizing token ring algorithm in the atomic state model. Self-stabilizing algorithms have 2 properties: convergence and closure. Convergence means that from an arbitrary initial configuration, the system eventually converges into legitimate configurations in finite time. Closure means that once the system is in the legitimate configuration, it will be in legitimate configurations forever. Because of these 2 properties, a self-stabilizing system can recover from any transient fault. Take the following figure as an example. Suppose that from time step 1, the system is in the first configuration 1, which is in an illegitimate configuration. By taking 5 steps, the system reaches legitimate configuration 6. After that, the system never leaves legitimate configurations. However, sometimes convergence and closure properties are too strict to achieve in some circumstances, so some sorts of relaxations are made by researchers to deal with such situations. The one we use in this paper is called Loose-Stabilization, which relaxes the closure property of self-stabilization. Loose-stabilization is first proposed by Sudo and his co-workers. In their paper, they introduced this notion and applied it on the leader election problem in the population model. In loose-stabilization, the convergence property is the same with self-stabilization. Starting from any configuration, the system eventually reaches legitimate configurations in finite time. On the other hand, the algorithm can deviate from legitimate configurations after being in legitimate configurations for a very long time. The time the system needs to converge is called the convergence time, and the duration that the system stays legitimate is called the holding time. A loosely stabilizing algorithm is practically equivalent to self-stabilization if the holding time is much longer than the convergence time. For example, in this figure, the system reaches legitimate configuration 4 from an arbitrary initial illegitimate configuration 1 in 3 steps. After that, the system stays in legitimate configurations from 4 to 12 for example, 100 time steps. At next step, due to some probabilistic circumstance, the system deviates from legitimate configurations 12 to the illegitimate configuration 13. By taking 3 steps, the system goes back to legitimate configuration 10. In this execution, the convergence time is 3 and the holding time is 100. In the second part, I will describe the problem we try to solve in this paper. The maximal independent set problem with unreliable communications. First, I will briefly explain what maximal independent set (MIS) is. Consider a network. An independent set is a set of nodes in the network that are not adjacent to each other. And a maximal independent set is an independent set that all nodes that are not in the independent set are adjacent to at least one node in the independent set. For example, in the left figure, the set of green nodes is a non-independent set because some of the nodes in the set are adjacent to each other. In the middle figure, the set of green nodes is an independent set but not maximal because some white nodes are not adjacent to any green nodes. And in the right figure, the set of green nodes is an MIS because two conditions are both satisfied. Second, I will briefly talk about the computational model. In this paper, we used uniformly random distributed scheduler in the atomic state model. At each time step, each process is independently activated by the scheduler with a constant probability phi. If process P is activated at step T, it reads the states of all its neighbors and its own, then does some local computations, at last updates its state if necessary. Next, we introduce the unreliable communications. For any pair of processes, say A and B, when process A reads the state of B, with a constant probability rho, the value that A gets from B is erroneous. For example, the state of B is 0, and the domain is the set 0 and 1. With probability rho, A will get incorrect value 1 from B, and with probability 1 minus 0, A will get the correct value 0. The distribution of the erroneous value is divided into two types: uniform distribution and arbitrary distribution. With uniform distribution, the erroneous value is uniformly distributed on the domain. For example, if the domain is a set from 0 to k and the correct state should be 0, then the incorrect value will be 1 or 2 or 2k with probability 1 over k. And in arbitrary distribution, the erroneous value has no constraints. Now let's see the third part. In this part, I will show you the results of the proposed algorithms along with the assumptions. Based on the way we designed the algorithms, the three approaches are called the redundant state approach, the step-up approach, and the repetition approach. In the following table, n is the number of processes in the network. D is a sufficiently large constant. Delta is the maximum degree of processes, and the topology of the network is arbitrary. In the redundant state approach, we do not need the ID, but we require that the maximum degree of processes to be constant, and the error caused by the unreliable communications is uniformly distributed in the domain. The maximum expected convergence time of this approach is O log n. The minimum expected holding time is omega into d, and the space complexity of each process is O log n. In the step-up approach, we also do not need the ID, and there is no restriction on the maximum degree of processes, and the error distribution is also uniform. The maximum expected convergence time of step-up approach is O n times log n to 3 to the power of 3, and the minimum holding time, expected holding time, is in omega n to d. The space complexity of each process is O log n. In the repetition approach, unique ID for each process is needed, and the maximum degree is arbitrary, and there is no restriction on the error distribution. The maximum expected convergence time of repetition approach is O n squared time log n. The minimum expected holding time is e to omega n. The space complexity of each process is O n times delta times log n. Next, I will give the loosely stabilizing approaches to solve MAS with unreliable communications. Before introducing the exact approaches, I will at first present a fundamental approach with reliable communications and show you that how do unreliable communications cause trouble. A simple centralized self-stabilizing MAS algorithm works as follows. It has two rules. In rule 1, for a process A, if A is white and for each neighbor P of A such that P is also white, then A colors itself to green. In rule 2, if A is green and there exists at least one neighbor P of A such that P is also green, then A decolors itself to white. At the end of the algorithm, the set of green nodes is a maximal independent set. However, if we introduce unreliable communications, the self-stabilizing solution for MAS is precluded. It can be easily proved by the standard partition-based argument. Consider a network consisting of two processes, A and B, and one link between the processes. In a legitimate configuration where A is independent and B is dominated, when B tries to read the state of A, the result that B gets may be corrupted in the link by the adversary, and B cannot get the correct information of A. Hence, B decides to change its state to become an independent process, which leads to an illegitimate configuration. To circumvent such impossibility of self-stabilization in probabilistic error models, we focus on Loose-Stabilization and proposed 3 approaches: the redundant state approach, the step-up approach, and the repetition approach. The first one is the redundant state approach. The assumption of redundant state approach is that the network is anonymous, the maximum process degree is constant, and the error distribution is uniform. The key idea of this approach is that besides using 2 states to represent independent and dominated processes, we introduce C-1 redundant states, where C is theta d to n, theta n to d plus 1, and d is a sufficiently large constant to confine the effect of erroneous communications. And we let states 0 and C represent independent and dominated processes, respectively. Take a pair of processes A and B as an example. In the fundamental approach, there are only 2 states, say 0 and 1. Suppose that now process A is in state 1 and process B is in state 0. Then the probability that A erroneously reads 1 from B is a constant rho. Recall that rho is the error probability caused by unreliable communications. Now we introduce the set of states from 1 to C-1 as redundant states, and states 0 and C as the meaningful states. Let the state of A be value C and the state of B be 0. Then the probability that A erroneously reads the meaningful state C from B is a very small probability rho over C, which is close to 0. In other words, the erroneous value can be detected and does not cause any incorrect effect to the receiver A with high probability. This mechanism allows processes to greatly confine the influence from erroneous communications and make appropriate actions. Next, we talk about step-up approach. The assumption of step-up approach is that the network is anonymous and the maximum process degree is arbitrary. The error distribution is also uniform. To circumvent the constraint of bounded degree in the redundant state approach, the step-up approach makes better use of the redundant values. In the previous approach, we only use the redundant values to reduce the effect of corrupted information, and we do not care about what the exact values are. While in this approach, processes confine the effect of corrupted information by utilizing the redundant values as buffer. When processes read information from the neighbors, they change their states step by step so that even if some of the steps are erroneous, such steps have less influence and processes can correct their moves before causing larger influence with high probability. For example, suppose process A is in state 0. In next 2 moves, it gets incorrect values from its neighbors and makes erroneous moves. Instead of changing its state directly to C, it first increases its state to 1, then to 2. At the 3rd move, it gets the right information and corrects its state back to 0. We can prove that the probability that a process keeps making erroneous moves for many times is extremely small. Next, we introduce the repetition approach. The assumption of repetition approach is that the network is identified, and the error distribution is also arbitrary. And the maximum process degree is arbitrary. And the error probability rho is less than 1/2. Different from the previous two approaches, the repetition approach does not use the redundant values. The key idea of this approach is the error correction by a very simple repetition code with majority decoding. The assumption of rho is less than 1/2 admits an error correction with high probability for a sufficiently large number of repetitions, 2k plus 1, where k is theta n. While the error probability when reading once is 0. The repetition code works without any synchronization mechanism except for the period around the time when the encoded value changes. Thus, it keeps a long holding time after the states of all processes stabilize. In the convergence period, however, the change of processes states would cause the failure of error correction with an unexpectedly high probability. To prevent such failure, we install an additional mechanism of priority-based monotone fixing of processes states, where the unique ID for each process is needed. Compared with the error-free case, it uses a longer convergence time, but it is still polynomial of n. Next, we will give the summary and future work. In summary, we applied Loose-Stabilization on the atomic state model for the first time, and proposed the loosely stabilizing algorithms for MAS with unreliable communications, and analyzed the performance of the approaches. For the future work, we will try to improve the time complexity of the algorithms, analyze the lower bound, and find other applications of loose stabilization on the atomic state model. Here are the references used in this video. And this is the end of the video. Thank you for watching.